I'm going to give you some tips for Post-Lab 23, stereochemistry of bromine addition to trans-cinnamic acid. First, you're going to report the melting point of your product and the identity of your product. Your possible products are the erythro or thrio isomers. They have really different melting points. They're listed in table 23.1 in your textbook on page 203. And this should be a pretty simple identity because the melting points are different by about 100 degrees. Then you have a couple questions from the textbook. Question number 5 is one of those ones where it's giving you a few different possible mistakes that you could have made in lab and asking you to think about how that would have affected the outcome of the experiment. So first, it's saying, what if instead of using trans-cinnamic acid, you use a mixture of cis and trans-cinnamic acid? How would that affect? You want to be thinking about purity. You want to be thinking about effective yield, things like that. Part B is asking if you added 5 milliliters of bromine solution instead of whatever the lab told you to add, a different volume. And then 6 is asking what if you used cyclohexane instead of cyclohexene. For exercise 7, which is question 3 on your post lab, it's asking you to draw, it says stereochemical projection. Stereochemical projection. This just means that it's asking you to draw structures that show the stereochemistry, which means you want to use wedges and dashes to show the stereochem. Or actually, you don't have to do it that way. You could also use Fisher projection. That would work as well. Or you could use a Newman projection, but that would probably be pretty tricky. So it's asking you to just use some sort of notation that's going to show the stereochemistry of the products of the reaction. And it's asking you, this question is actually really not totally related to the experiment that you did. It's asking you basically if you did the bromine addition to, instead of trans-cinnamic acid, you did it with maleic acid or fumaric acid. It's just two different situations. And it's telling you, it's giving you like a condensed structure for maleic and fumaric acid. Funny notation. These are the cis and trans isomers of this molecule. So this would be the trans isomer. You want to think about what it would look like, what the product of bromination would look like for the trans isomer, and then also what would the product be or products be for the cis isomer. Next, you have exercise 8, which is kind of a follow-up to this exercise 7. It's asking you two parts, part A and also part B. Could you resolve, which is the same thing as separating, so could you separate enantiomers from each other? Part A of this question is actually asking about the experiment that you did, the bromination of trans-cinnamic acid. It's asking you, is the product optically active? Optically active means that the molecule has at least one chiral carbon and also no plane of symmetry. If you have chiral carbons but a plane of symmetry, then the molecule is meso and it's not optically active. So it's asking, is it optically active? Is there at least one chiral carbon and is there no plane of symmetry? And then it's asking, could it be resolved? Could the product be resolved into optically active constituents? So just to kind of really simplify, let's just say you did a reaction where you produced an R molecule and then also an S molecule. It could be possible to separate those, I'm going to try to find a way to notate this, to separate the R molecule from the S molecule using some sort of separation technique. So the question is asking, if you end up in this experiment, if you end up with a mixture of enantiomers, if you end up with a mixture of R and S, is it possible for you to separate those two from each other? Now obviously if you only produced one enantiomer, if you only made one thing, it's not going to be possible to separate that one thing into two things, so it's something to keep in mind. And then for part B of this same question, it's asking you the same thing, but for the bromination of fumaric acid, which is one of the things you sketched out in question number 3. Same thing. If it's optically active, could you separate it into separate enantiomers? And of course, first of all, it would have to be optically active, and second of all, there'd have to be at least 2 things in order for you to separate them. The last thing you're going to do here is one of these flow diagrams. This one's actually pretty easy compared to some of the ones that you've done in the past. You've started with 3 things, you performed some sort of reaction, and you came up with 3 new molecules. Notice that I'm including leftovers, just sort of lumping them all together. So the 3 things that you've listed here are not necessarily going to be the 3 things that show up after the reaction takes place. This is where molecules are being converted. Vacuum filtration is just a separation technique. It's not a reaction, which means that all 3 of these substances need to appear exactly the same in the boxes down here. All that you're doing is separating these 3 things from each other.